recorded. Or sometimes I record it and then there's no sound for some reason. I don't but yeah. Right, so this is the last lecture for this semester. Next week we'll have the revision. We'll wrap up with sound. So we've been talking about waves. We started by discussing simple harmonic motion, the oscillation of particles. And then when that oscillation propagates, you have the wave, and the wave carries with it energy as it propagates. And then last time, we also learned about the two kinds of waves, transverse wave and longitudinal wave, and they're classified depending on the direction of propagation relative to the vibration direction. So for longitudinal waves, we learned that the wave propagates parallel to the vibration of the oscillating particles. And so, for example, here you have this plunger that pushes air inside the column, and that's how the wave propagates. It's the compression and expansion of the air molecules in the column. So it's sort of, sound is a longitudinal wave, so it works similarly. I don't know if you've ever tried putting your hand in front of a speaker, especially if the speaker is in full blast. You'd usually feel the vibration of the diaphragm of the speaker. So that vibration vibrates the surrounding air molecules. The air molecules expand and contract, and they bump into neighboring air molecules, and the sound starts to propagate through the compression and expansion of the air molecules until it reaches our ear. Okay? And then the sound wave then vibrates our eardrums, and that's how we perceive sound. Yeah, so that means that sound waves, the propagation of sound waves, just like all longitudinal waves, will depend on the properties of the medium. Longitudinal waves will need a medium in order to propagate because it needs the expansion and contraction of the medium. Yeah, so it depends on the properties of the medium. Specifically, it depends on the compressibility of the medium, right? So the longitudinal wave propagates through the expansion and compression of the medium. So yeah, the compressibility of the medium will affect how the sound propagates, as well as all longitudinal waves. It also depends on the density of the medium. If your medium is quite thick and heavy and dense, as opposed to light. So when we were talking about the elastic properties of the materials, we learned about the Young's modulus of elasticity, which tells us how easily an object can be deformed. So it's sort of, in a way, the compressibility is embodied by the Young's modulus, the modulus of the material. For liquids and gases, it's the bulk modulus B, okay, and the density rho. This is how the speed is related to the compressibility and the density of the material. And for solids, you have the Young's modulus. So similar form, the compressibility is just given different names depending on whether your medium is liquid and gas, in which case it's the bulk modulus. If it's a solid medium, then you just call it the Young's modulus. But it's a property of the material. You can look it up in the table. Yeah. So this speed here relates how fast the wave travels relative to the medium, but you can also use the equation that we learned to find the speed in relation to the wavelength and the frequency. So speed is still equal to wavelength and frequency. So usually, if you have a wave that's propagating through a material and you know the properties of the material, you can find the speed through this equation relating the speed to the properties of the material. And then from that speed, you can determine the wavelength, okay, of the wave. Okay. So all these equations still hold for sound waves. For sound waves, there are two aspects of sound waves. We can describe them in terms of their pitch and their loudness. So when we say pitch refers to whether the sound is high, so it's or low pitched sound. All right, so high or low. If we relate the pitch to the physical property of the wave, pitch is determined by the frequency of the wave. So high frequency waves have high pitch. When we say high frequency, you have more crests or troughs passing a given point per unit time compared to a low frequency sound. You have less number of crests or troughs passing a given point per unit time. Okay. All right. For our ear is only sensitive to 20 hertz to 20 kilohertz frequency sound, and that ability usually degrades with age. So yeah, the younger we are, less than 20, you can, yeah, the research says up to 20, you can hear up to 20 kilohertz, and then the older you get, this upper range sort of decreases, and you get less annoyed with high frequency sound compared to when you were younger. Uh, so there's actually, I don't know if you've heard of those sound devices that's in the market that's used to scare away rats and rodents and pests from the home, and they emit this high frequency sound. Um, they have a similar thing. Let's try to see if this will work. Called the mosquito. If the Wi-Fi will work here. It's quite... Volume. Can you hear that? I can't. I can't. So yeah, so that's the mosquito sound. Yeah. I can't hear him, and obviously. Yeah. But I think when this came out, there was a ringtone. I mean, some teenagers use it as their ringtone. So to like try to hide texting during class so their teacher won't hear it. But then all their classmates can hear it and everyone was annoyed. And so they outed like,
the secret of Rob's great teeth.
So they sort of outed the students who are using the mosquito sound for the ringtone. But yeah. So the ability of the ear to hear high pitch or high frequency sound sort of degrades over time. And yeah, when you go for an audiology test, that's what they test, that you hear high frequency sounds. Okay, and the other aspect of sound is loudness. So we can classify sound in terms of their loudness. When we say loudness, it's the intensity of the sound. And we'll go into more detail into each of these aspects. So the human ear can detect intensity of 10 to the minus 12 to 1 watts per meter squared. And we'll go more into detail about this intensity range later on. But first, let's talk about pitch. Right, so using the audible range for human hearing, 20 hertz to 20 kilohertz, as the reference frequency range, we can classify um, frequencies into three classifications. So the audible waves, that's what is audible to the human ear. Frequencies less than the audible range are called infrasonic waves. That's what earthquakes have low frequency sound, giraffes. And that's why some animals can detect when there's an earthquake coming, um, because they can actually hear it, but we can't. It's outside of the audible range. Frequencies that are above the audible range are ultrasonic waves. Okay. These are the really high pitched sounds that, that, that we cannot hear, right? Okay, so the frequency determines pitch. It determines how high the sound that we can hear. But sometimes the frequency can change depending on whether the observer, us, or the source is moving. And that phenomenon where the frequency changes relative to the motion of the observer or the source is called the Doppler effect. So the Doppler effect says that the frequency will change when the source, the source of the sound, or the receiver or detector moves relative to the medium. And so, for example, you have this stationary fire truck that's emitting sound. Okay, the sound will emit in all directions. And the frequency, the pitch of the sound will be the same in all directions, so that a person in front or at the back will hear the same pitch. But when the fire truck starts to move, Doppler effect says that the frequency the frequency of the sound in front will be different from the frequency of the sound at the back. This diagram probably illustrates it better. So the blue lines here are the wave, like you can think of them as the crests of the waves, of the sound wave. So see how they are closely spaced compared to the back waves, which are farther apart. That means, so which part here will have a higher pitch? Which person will hear a higher pitch? Is it the person in front or the person at the back? Yeah. Okay. So the wave in front will have a higher frequency because the crests are more closely spaced. You have more crests passing a certain point per given time. So this person in front will hear a higher pitch compared to the person at the back. So so let's try to simulate that. I'm sorry to annoy you. If you're quite sensitive with a high-pitched sound, yeah, I'll give you fair warning. You can leave the room. But yeah. Otherwise, I'll turn this on and we'll try to see Doppler effect. Okay, so just that stationary, we can all hear the same pitch. It's that annoying high frequency pitch. If I try to whirl this around, hopefully it will not come off, but yeah. But can you detect how the pitch changes? Yeah. So while it's moving toward you, while the source is moving towards you, it has a higher pitch because you have like, it's sort of you have this closely spaced compression of the medium. Moving away from you, you have a lower pitch. So Doppler's effect. If we want to, yeah, so if the source is moving towards the observer, you hear a higher frequency sound. Okay. A higher frequency sound means shorter wavelengths. The relationship between frequency and wavelength are inverse. Remember how speed? Yeah, remember how speed is equal to frequency times the wavelength? Okay. And this speed is also determined by the medium. So the higher the frequency, the smaller the wavelength. And if the source is moving away from the observer, like this observer at the back of the fire truck, then this observer will hear a lower pitch because the waves will have lower frequency. Lower frequency means higher, longer wavelength. Right? Cool. So if we wanted to quantify the frequency, like what is the new frequency if the source or the observer are moving, then we have this equation that will help us solve what the new frequency is. So this F prime here, you read this as prime, but we can just put new frequency is equal to the old frequency when the observer and source are stationary times this whole term in the bracket that takes into account the movement of the source and the observer. Right, so this V sound here, this is the speed of the sound that depends on the properties of the medium. Okay. And it's usually fixed. So if yeah, this is the speed of the sound that depends on the properties of the medium. It's the speed that you calculate from, for example, the beta or the Young's modulus over the density. Okay. So that is sort of this sound, speed of the sound is sort of fixed for a given medium and a given temperature. So for example, the speed of sound in air is 343, I don't know what we're using. It's 343 meters per second in air. This V observer, that's the speed of the observer or the person or the detector that's receiving the sound. This is the V source, that's the speed of the source of sound. So here you have this plus minus on top and this minus plus at the bottom. You just choose either of these symbols. So if you chose V sound plus V observer on top, you should use V sound minus V source at the bottom. So the top sign is used for motion when the observer or the source moves towards each other because when the source or the observer is moving towards each other, the frequency increases. Okay. Right, so I'll just let you write that down and then that's quite important, knowing which signs to use. right? So if we look at this figure here, when the source is moving, or the source or the observer are moving towards each other, notice how the frequency increases. Okay? And so you should have a higher frequency when the source or the observer are moving towards each other. So that means that the top part, you should add the speeds so that you have a large number on top, and you should subtract the speeds at the bottom so you have a smaller number at the bottom. So in short, if it's moving towards, right, so towards, the equation becomes new frequency is equal to V sound, the speed of sound. Again, that depends on the medium. And so if the sound is just moving in air, V sound will always be 343 meters per second at 20 degrees Celsius. Plus V observer divided by V sound minus V source times the old frequency. So that's how the equation looks like if either the source or the observer or both are moving towards each other, such that the frequency increases um, via Doppler effect. Okay? And if either the source or the observer or both are moving away from each other, okay, so movement away from each other, the equation should give you a smaller frequency. Okay, because movement away will decrease the frequency, as you can see in this figure, behind the fire truck. And so the equation that you use should give you a smaller frequency. So that will be V sound minus V observer on top, right, divided by V sound plus V source at the bottom times the old frequency. Okay, so don't forget to multiply the bracket with the old frequency. Usually that's commonly forgotten, but right. So how you use this Doppler equation, first you have to determine whether the frequency should increase as a result of the movement. If the answer is yes, then you use the equation that will give you a higher frequency. Right? If the movement will result to a lower frequency, okay, then you use the second equation that will result to a lower frequency. Right. So let's try to practice that concept by looking at this example. A railway train is traveling at 20 meters per second, and the frequency of the note emitted by the engine whistle is 500 hertz. The speed of sound in air is 343 meters per second. What's the frequency heard by a stationary listener in front of the train, behind the train, and then what's the wavelength of the sound in front and behind? So of course, if it's stationary, then speed is zero. Okay, it's not moving. So yeah, take that into consideration in your solution. Okay, so let's try to decipher the question and then look at the solutions. Um, so it says here that the listener is stationary. So that means that the speed of the observer is zero. Okay, that will simplify the equation. The train, so in front of the train, that means that you have a stationary listener and then the train is approaching them. That means that the train is moving towards the listener. Okay. And movement of the source towards the listener will increase the frequency. Right? That means you use the minus sign at the bottom, V sound minus V source. The speed of the observer, that's zero, so that's already taken out of this simplified equation. So you only need the speed of the sound and the speed of the source and the old frequency. What's the speed of the sound? That's the speed of the sound in air. Okay. The speed that depends on the medium. And for air, if the sound travels through air, that speed will be 343 meters per second. So it's probably one of those, yeah, we'll consider as constants that's worth remembering. Yeah. Okay, and then the speed of the source, the speed of the train is given in the question. That the speed of the sound is the same, it's the same medium. And the original frequency is 500 hertz. So in your calculation, if you get like a higher frequency, try to check whether your answer makes sense. Okay, the train is moving towards the listener, so that means the frequency should be higher, and so the number that you get should be higher. Behind the train, so the train is now moving away from the listener, so that means the frequency observed by the listener should decrease, in which case the Doppler equation um, becomes V sound over V sound plus V source. Again, the listener is stationary, so V observer is equal to zero. So this one. For both cases. Okay. V sound, that's the speed of sound in air, 343 meters per second. Okay, the source is still traveling, the train is still traveling at the same speed, 20. Okay, and the old frequency is still 500 hertz. Again, do a sanity check. Okay, you know that as the train moves away from the listeners, the frequency should decrease. So the new frequency should be smaller than the original frequency. Right. So now when you calculate the wavelengths of the sound waves, okay, you use V is equal to lambda F. It's the equation that relates the speed of any wave to its wavelength and frequency. Okay, the speed here is the speed of the sound wave, 343 meters per second. You've calculated the new frequencies f. So you can rearrange, you need to rearrange this equation to isolate lambda, which gives you the speed divided by the frequency. Same procedure for both, just different frequencies in front and behind the trains. Any question about the solution? So it's usually it's yeah, the first step really is to try to determine whether something one speed is zero, to simplify the equation, and then try to determine whether the frequency should increase or decrease. I think that's the most crucial point, is whether the frequency should increase or decrease, because that will determine which equation you will use, which form of the Doppler effect equation you will use in your calculation. Right? Also, the other aspect of sound is the loudness. Loudness is related to the intensity. Okay, so what is intensity? Intensity is defined as the energy per time transported over a unit area. So remember how waves, they carry with them energy as they propagate through space. So the amount of energy that the waves carry per unit time across a given area, a unit area, is called the intensity. Mathematically, then it's energy per time over area. Energy per time, you already encountered this when we were talking about heat. Okay, that's joules per second, and joules per second has a unit of watts, which is called the power. So intensity equals power over area with units of watts per meter squared. So the units for power is watts, unit for area, meter squared. The question here is, what is this area? What's the area? Okay. To imagine what the area is, imagine how sound propagates. Consider like a point source of sound. And this sound will propagate all throughout space, like in 360 degrees. That's why if you have a speaker in the middle, everyone around it can hear the sound equally. So the sound will propagate through space. It's three-dimensional. So you can think of the propagation as spheres centered around the source of sound. It's sort of similar to, how ripples in a calm lake propagates. It propagates as spheres. I mean, although this is two-dimensional, for sound, just extend that to three-dimensional. So you have spheres propagating away from the source of sound. And the power will be, or the energy per time will be distributed equally through the area of the sphere. And so the area in our equation for power, the area will be the surface area of the sphere. Which is 4 pi r squared. R is the radius. Radius of the sphere. Okay. Right, and power, that's the power at the source. Okay. Right. The assumption is no energy is lost, it's conserved, so the power will always be the same regardless of the distance from the source. So here, the intensity is inversely proportional to R squared. We call that the inverse square law. That means that the how loud the sound is decreases quite quickly as you go farther away from the source. It's a 1 over R squared dependence. Right? And perhaps to appreciate this inverse square law and how the intensity quickly decreases as a function of distance from the source, let's look at this example, which will also give us some practice in using the equation. So you have a point source that emits sound waves. The intensity 4 meters away is 0.448 watts per meter squared. What is the power emitted by the source? Right, so intensity equals power over area. We want to find the power, so we need to rearrange this equation to isolate power. Get rid of the area by multiplying both sides with area. So power equals intensity times area. What is the area? That's the area of the surface area of the sphere around which the sound is energy is uniformly distributed. So the power equals intensity times 4 pi r squared. The next question is, what is R? I mean, intensity is given 0.4482 watts per meter squared. That's the intensity that's given. What is R, which is the radius of the sphere? If this is your point source, right, and we say that the sound propagates as spheres centered around the point source, okay, then the radius of that sphere will be how far away you're trying to find the intensity for. So if you're trying to find the intensity 4 meters away, then that will be the radius of the sphere, right? 4 meters will be the radius of the sphere. Right? So then you have intensity 0.448 times 4 times pi times the radius 4 squared. Gives you 90 watts for the power. Okay. Right, and then what if you're 8 meters away from the source? So you double the distance. Okay. From 4 meters, you go to 8 meters. Okay. How quickly will the intensity change if you double the distance? What will be the new intensity. If we did the same calculation, okay, the power is the same. It's the power at the source. So it will be the same power that you've solved earlier, this 90 watts, that's the power at the source. What changes is the intensity as you go farther away from the source. Okay. Right, so power is the same, still 90 watts. The radius of the sphere will now be different because you're farther away from the source. You want to measure at 8 meters away from the source, so that's 8 squared. Will give you an intensity of 0.112 watts per meter squared. So comparing that new intensity 8 meters away to the intensity 4 meters away, doubling the distance results to a decrease of a factor 4 because of this r squared relationship. Double the distance, that means 2 raised to the power of 2 is 4. That means the intensity should decrease. So loudness decreases quite quickly over distance from the source. Okay. But the human ear is quite dynamic in the range of intensities that it can detect. Like we can hear like a whisper, and at the same time, which is a very, very small intensity. At the same time, we can hear, a jet plane flying by, which is very loud. Okay, so the human ear can detect sounds in a wide range of intensities. 10 to the minus 12, very soft, to 1, which is very loud. And because of this wide range, we perceive loudness as in a logarithmic way. Okay? And so it's easier to deal with this wide range of intensities. It's easier to deal with decibels, which is the logarithmic way of expressing intensity. And the decibel intensity is what we call intensity levels. So intensity level, I've underlined it here because intensity level with the word level is quite different to just intensity by itself. So when you read intensity level, that means that's the logarithmic scale, which is in decibels. And we'll look at decibels in the next slide. But yeah, whereas intensity, just intensity by itself, that's in watts per meter squared. Intensity level, that's the decibels unit. Right, so logarithmic scale of expressing intensity level, we use the symbol beta to indicate intensity, that indicate that we're talking about intensity level as opposed to intensity I. So the intensity level beta measured in units of decibels is equal to 10 log of the intensity over the intensity 0. Yeah. So that's the perceived loudness of sound that the ear perceives in a logarithmic scale. Perceived loudness. Okay, so let's take apart this equation here. I0, that's called a reference intensity. That's the threshold of hearing. So the lower limit for the sound intensity that the human ear can hear. That's assuming a perfect hearing. Okay. I, that's the intensity of the sound whose level you want to determine. Right. So beta, that's intensity level. Yeah. That beta there, that beta is intensity level. I, that's the intensity that you want to determine usually. I0, that's constant. Okay, that's always 1 times 10 to the minus 12 watts per meter squared. Yeah. So really, this equation relates the intensity I to the intensity level beta, because I0 is just a number, which is always 1 times 10 to the minus 12. Okay. Right, and that's why we were learning about logarithms yesterday, because we will need that to manipulate this equation to find the intensity. We need to be able to get rid of log. Right? And this example gives us some practice to do that. A point source of sound has a power of 4 milliwatts. Okay, so be careful there. That's milliwatts. 4 times 10 to the minus 3 watts. What is the intensity 2 meters away? Okay, very similar to the example we looked at earlier, relating power and intensity and the surface area of the sphere. What is the intensity 2 meters away? And then the next question is, what is the sound level, intensity level in decibels at that distance, meaning 2 meters away? These are some useful information. Hopefully they're useful. This is power over the area. Yeah. So the first one, intensity equals power over area. Straightforward, the substitution, the power is 4 times 10 to the minus 3. So be careful with that milli, prefix milli. And then the radius will be how far away you are from the source. Right? Thinking about the propagation of sound as spheres centered around the source. So you have 4 times pi times r, which is 2 raised to the power of 2. So you get the intensity 2 meters away, 8 times 10 to the minus 5 watts. You use that in the next question to find the sound level. So the intensity level has the equation 10 log I over I0. That means you need the intensity in order to find the level, intensity level. Okay. Right. So intensity will come from your previous calculation, 8 times 10 to the minus 5. I0, that's the threshold of hearing. It's constant. It's always 1 times 10 to the minus 12. Right. When I say constant, I mean, it's the same number that we will use in the calculation. Right? Yeah. You divide this to 8 times 10 to the minus 5 divided by 1 times 10 to the minus 12. Get the log of that and then multiply by 10. You should get 79 decibels. So at this stage in this question, there was no rearranging that was required yet for manipulating the logarithm. Okay. And in the next question, we'll look at how we manipulate the logarithm to find the intensity I if we're given the level beta. Okay. So a mosquito buzzes at 40 decibels. Calculate the intensity in watts per meter squared. So beta is given, you want I. Yeah, and this log equation relates the decibels to the watts per meter squared. Okay, but you need to isolate I by itself. Another question before that says 10 log. Do you have to put 10 log in the calculator or just log? 10 times log of the numbers in the bracket. Oh, yeah. Okay, so let's work through this. So before you can get rid of the log, so you probably hopefully you already have the idea that for you to isolate I, you need to get rid of the log. Okay, before you can get rid of the log by doing an exponential function, you need to have log by itself, meaning you have to get rid of this 10 because it's 10 times the log of I over I naught. And so you have to get rid of this 10 first by dividing both sides by 10. Right? And I naught is always 1 times 10 to the minus 12. Okay, so you need to divide both sides by 10 first in order for log to be just by itself on one side of the equation. Yeah. Okay, so once you have gotten rid of the 10 and log is just by itself. So this whole thing, this is in brackets. So you cannot really separate the log from I divided by 1 times 10 to the minus 12. But yesterday we learned how to get rid of the log. Okay, if you have x is equal to log y, if you raise both sides to the power of 10, okay, so if you do a base 10, essentially if you put 10 on, yeah, on both sides of the equation so that x becomes the exponent of base 10 and log y becomes the exponent of base 10. Okay, this base 10 will cancel out the log. So 10 exponent log y is just equal to y. 10 exponent x remains as 10 exponent x. Yeah. This was, yeah, yesterday's, we saw this yesterday. So that if you do the reverse, for example, you do log on both sides. Yeah, maybe I won't confuse you with that for now. So here, to get rid of the log, you put a base 10. Okay. So how do you do that here? You essentially put base 10 like we did here. You literally, if you put a base 10 underneath them, so this base 10 will undo the log, and you only have what's inside the bracket of the log, I1 divided by I1 times 10 to the minus 12. And then on the left hand side, you have the base 10, and the exponent is this 40 divided by 10. Right, so this is just one number, 10 exponent 40 divided by 10, or 10 exponent 4. That's just one number, and then 1 times 10 to the minus 12, that's just another number. So to isolate I1, you need to get rid of 1 times 10 to the minus 12 on the right-hand side of the equation. Right? It's a division, so you do the reverse of a division. If you multiply both sides by 1 times 10 to the minus 12, okay, that will essentially cancel the denominator here. So you have I is equal to 1 times 10 to the minus 12 times 10 exponent 40 divided by 10, which is 4. Yeah, you do the multiplication, that will give you the intensity. 1 times 10 to the minus 8. All right. And just one final point, which is quite important. Now, if a second mosquito sits by the first one and they're buzzing at the same level of 40 decibels, and you want to find the new intensity level in decibels. Right, so notice here, you might think that, okay, one mosquito has 40 decibels. You have a second mosquito at 40 decibels. Oh, so I just add them up. So the total decibel will be 80 decibels, but that's an incorrect answer. So the correct answer is actually 43 decibels, not 80 decibels. Why is that? Okay, we can only add intensities and not intensity levels. Okay. So when you have more than one source of sound, you need to add the intensities before you convert that to intensity level. It's because the intensity is it's linear, but the intensity level it's logarithmic. So it's not a simple addition. So the new intensity, if you have two mosquitoes, will be twice the intensity of one. Okay. If it's the same intensity level, that implies that the intensity will be the same. I1 is equal to I2. And we work out that the intensity of one mosquito is 1 times 10 to the minus 8 in the previous question. So if you have two mosquitoes, the new intensity of them will be twice the intensity of a single mosquito. And once you have the intensity for both mosquitoes, that's when you convert that to decibels. Yeah. This will be the intensity 2 times 10 to the minus 8. I0 is always 1 times 10 to the minus 12. So you divide this 2 times 10 to the minus 8 divided by 1 times 10 to the minus 12. Get the log, multiply with 10, and you should get 43 decibels. Yeah, I know. I see your faces. Um, yeah, hopefully the workshop will give you more practice. It will become easier with practice. I, I promise. I mean, it looks scary because of the log and trying to get rid of the log, but sometimes you don't have to get rid of the log. Like in this example, right? You're given the intensity, you want to find beta. Um, and you didn't have to do any manipulation. But yeah. So a 10-minute break, and then the workshop is in the last sheet, and you can work on it. Of course, I'll be here for questions if you need.